Okay, let's start. This is Rajat. I'm an assistant professor at UCT School of Biosystems and Food Engineering. I'm also the chair of the Agriculture and Food Engineering Division of Engineers Ireland. Welcome to this lunchtime webinar session jointly organized by the Agriculture and Food Division and the Energy, Environment and Climate Action Division of Engineers Ireland. I would like to thank my mentor, Pat Kiernan, who is the Director of Asset Management at Alternus Clean Energy, and Kate Markey. She is the Sector Support Executive of Engineers Ireland for contributing to the organization of this webinar. And last but not the least, my friend and colleague, Dr. Shu Ning. We also call her Shirley, who is an assistant professor of bioengineering for the circular bioeconomy at UCT School of Biosystems and Food Engineering, for agreeing to deliver her talk on bio-electrochemical pathways for biogas upgradation, optimizing feedstock to meet 2030 biomethane demand. She is an alumna of Tongji, Tsinghua, and University College Cork. She is also a visiting scholar at MIT, and she leads major national biogas projects. And the list of awards is very big, so I'm trying to make it short. This will be an 1 hour session, so the entire talk will be recorded. The technical part of the talk will be approximately 30 minutes, and that will be followed by a question answer session. So please write your questions in the question and answer chat option at the bottom of this screen, and Shirley will be happy to address them after her talk. So you can relax and enjoy her talk. Shirley, the floor is yours.
Yeah, thank you very much, Rajat, for your detailed introduction. And thank you very much for the invitation from Engineers Ireland for this opportunity to present my research. So today I won't make it very difficult. So half of my presentation will be I'll introduce the basic understanding of what is anaerobic digestion and what is the microbial electron synthesis, which is an innovative bioelectrochemical engineering process. And half of the presentation will be incorporated with my current ongoing research. So the topic of today's talk is the bioelectrochemical pathways for biogas upgradation. And the target is to optimize feedstocks to meet the 2030 biomethane demand. And firstly, may I introduce myself a little bit before the presentation? And currently, I'm a lecturer in the School of Biosystems and Food Engineering since last year in UCD. And previously, I was graduated and gained my PhD degree in engineering from University College Cork. And after that I have 2 years postdoc experience in the Research Ireland's Marai Research Center. And during that 2 years postdoc experience, I was co-leading two national projects. One is the eMERGE project focusing on the digested process from anaerobic digestion refinery platform. And the other ongoing SEAI project is about the CO2 valorization to value-added chemical products. And so the previous or current ongoing national projects are funded under Research Ireland and as well as the Sustainable Energy Authority of Ireland. So first of all, let's look into this interesting picture. What do we notice about the picture of the Earth at the night time? We can see some of the place all over the world is lightened, but the others not. So 1 in 10 people globally still lack of the access to electricity. And 2.5 billion people are still rely on the dirty fuels to heat their homes and cook their food. So there are some problems of the current world, including the disadvantaged communities, have been marginalized and overburdened by the underinvestment in infrastructure and lack of the access to technology. So my work is mainly based on bioelectrochemical engineering, and within this technology, we would be able to solve the problem of resource and energy equity, as well as produce more sustainable fuels and chemicals for the other unaffordable developed areas all over the world, as well as contribute to the development of circular bioeconomy. And my research ambition is to develop the bioengineering systems that are affordable, widely accessible, and the most important, sustainable. And the major themes of my research is all related to anaerobic digestion. So this process, the pre-treatment process of anaerobic digestion, will be the biomass valorization. We have a wide range of feedstocks feed into the anaerobic digesters, including the grass silage, cattle slurry, food waste. But which one would be the most efficient and most economic effective one? And the second part area of my research is the focusing on the digested produced from anaerobic digestion, which is can be processed through hydrolysis or hydrothermal carbonization into biochar. I'll explain what is biochar in the next few slides. And the third one is the bioelectrochemical biorefinery. You can simply understand as the CO2 feed into the bioreactors, and the microorganisms can eat CO2 and then convert it into biomethane, liquid biofuels, or other valuable chemical commodities. And the fourth part, the last but not the least, is the 3D printed bioelectrode optimization, especially used in the bioelectrochemical biorefinery platform. So the first part of my research I would like to highlight today is the circular bioeconomy systems based on anaerobic digestion. See a very interesting news today, this morning, from the Irish Times. It says that why 2026 could be the biomethane's big year. It says that for 2026, Ireland will get on track to scale up the generation of the green gas biomethane using agricultural and food waste. And I know that the Copenhagen Infrastructure Partners, which is called the CIP, is planning to build 7 in total large-scale anaerobic digesters, which will be able to deliver a third of the national 2030 target of about 10% of Ireland's natural gas demand. And there's the target set in the Repower EU plan is that by 2030, we need to have 35 billion cubic meters of biomethane, which is a tenfold increase as compared to the methane production in 2021. An anaerobic digestion process can be mainly divided into 4 steps, including the hydrolysis, acidogenesis, and the final 2 steps included was the methanogenesis. And so by these 4 steps, the complex substrates will be first divided into monomers and then be degraded into propionate butyrate, which is the mix of volatile fatty acids. And then VFAs can be finally degraded into by methanogenogens to produce biomethane. So the future AD anaerobic digestion plant is not only for biogas production, but actually it is a very, very good integrated circular cascading systems for negative carbon emission. So within the anaerobic digestion platform, the digested produced through it can be used as the fertilizer for farmers or can be pyrolyzed into biochar, and the biochar will be added back into the biomethanation process for more methane production. And so the cascading circular bioeconomy system is based on anaerobic digestion. That's what I'm trying to develop in the future scenario. And so here it comes, what is exactly the biochar? The biochar actually is a kind of carbonaceous material. It has large surface area with a very small volume. And for example, for the distillery process, the distillery byproducts will be fed into the lab scale anaerobic digester, and then we separated it, digested, and put it digested into the tube furnace or muffle furnace, and then within the specific temperature, the specific ramping time and holding time, we got different biochar with different properties. Then we will select the best biochar, and for the application of biochar, it can be in the aspects of environment as well as the energy. In the environment applications, biochar can be used to remove pollutants, used as the additives in anaerobic digestion process, used as the soil amendment or construction materials. But for energy, it is a very innovative perspective at the moment. Since the biochar has good electrical conductivity, it can be used as the replacement material for supercapacitors, batteries, hydrogen storage, as well as what I'm going to talk in the next few minutes, microbial electrosynthesis. And the process of anaerobic digestion, there are usually, we know about the single stage process, which the hydrolysis, acidogenesis, and methanogenesis are happened in one single reactor. It is very mature technology, well established with low investment cost, well understood the process. But in this process, the hydrolysis is not optimized is the most important challenging point I'd like to address here. But if we go into the four steps in the anaerobic digestion process, we find that there is a difference of the optimal pH for different microorganisms. For microorganisms, in the first two steps, for the acidogenesis and the which is included the hydrolytic bacteria and the acidolytic bacteria, the optimal pH is much lower, is 5.5. But for the final methanogenesis, methane production process, the arche's optimum temperature at optimum pH is 7.5, more neutral. So with the two-stage digesters, we would be able to separate the first two steps and the methanogenesis process and leave the microorganisms and the archaeas both grow in their optimal temperature and pH. So here we come to the two-stage anaerobic digesters. The hydrolysis and acidification are separated in the first reactor. So the first stage, we have 55-degree pH more acid with a short hydraulic retention time for the maximum volatile fatty acids production. And then the VFAs will be fed into the second stage, which has a lower temperature, a higher pH, and longer hydraulic retention times. So by developing the two-stage anaerobic digesters, it can enhance the process stability, optimize the hydrolysis process, get higher rate of substrate degradation, separate the produced gas, as well as shorten the overall retention time. So in my research, I investigated the biochar's performance in both the batch trials and continuous trials of single-stage anaerobic digestion. and two-stage anaerobic digestion. So the substrates I was used is the typical Irish feedstocks, including the grass silage and cattle slurry. And we feed the substrates, the mixed substrates, into single-stage reactor and two-stage reactor with or without biochar. We found the results that in single-stage digesters, with the biochar supplementation, we can get 10% of methane increase. And in two-stage digesters, we can see 50% of hydrogen production increase in the first stage and 25 methane increase within 10 gram per liter biochar supplement in the second stage reactor. So the specific methane production yield is listed in this figure, and we concluded two-stage AD is much better than the single-stage AD, and biochar supplemented is better than without biochar, and both the acidogenesis and methanogenesis process in two-stage digesters were enhanced by the biochar addition. And also the results from continuous anaerobic digestion, which is more similar to the actual industrial continuous anaerobic digestion operation. The same feedstock, the mix of grass silage and cattle slurry, and also the continuous experimental data of how much biohydrogen and biomethane produced in 80 days. So we concluded the continuous two-stage system still performed better than single-stage systems, and the biochar was found in this process to enhance the hydrolysis process, promote the biomethane production, and stabilize the pH in the digestion process. Then the next part is microbial electrosynthesis. We know that biogas is produced through anaerobic digestion process, and biogas consists of 40% of carbon dioxide and 60% of methane. So where does the 40% of biogenic CO2 go? If we look into our system, our electricity systems, we can find that there's a huge gap. We can get approximately 35% dispatched down electricity in our energy systems, and no arrow here to convert the electricity into useful compounds. So if we jump out of the circle of the traditional bioengineering, we find that the fundamental of bioengineering actually is the same. The bioengineering is about electrons. Where does the electron go? And for example, the traditional way how we fermented biomass for cellulose, for example, use cellulose make the ethanol or butanol. The most common performance is that the electrons are bound to the carbon directly. But now with the MES, the cool thing is that microbes, they can receive the extra electrons from electrode that you feed with the electricity, so they don't need to bond with the carbon directly. And this bioelectrochemical process in which the microbes use the electrons supplied by an electrode to convert the carbon dioxide into the other value-added chemicals, including biomethane. So what is MES? That's some basic understanding and the background of this specific term. So MES is an emerging one-step bioelectrochemical process, and the microbes convert CO2 into multi-carbon products, driven especially by the renewable electricity, typically from an electrode. And the advantage of this technology is that it contributes to surplus electricity storage to use the dispatch down electricity, and the cathode reduction of carbon dioxide can be coupled with anode waste oxidation, which is contribute to the remediation in environmental engineering. And the most important thing is totally CO2 neutral biorefinery platform. So that's how the MES can be cooperated with the traditional anaerobic digestion. So we have the typical feedstock feed into the anaerobic digesters. We have the biogas consist of 60% of methane and 40% of carbon dioxide. And the mixed gas can be directly fed into another bioreactor with a pair of electrodes inserted into it. And the digested, as I mentioned, can be a carbonaceous materials and might have the potential to replace the to make the supercapacitor or act as the electroconductive material or the electrode used in MES bioreactors. And then the CO2 can convert it into value-added products at the surface of the cathode, including biomethane, liquid biofuels, and chemical commodities, and contributed in different sectors, including the electricity, heating, shipping, and the other transportation and food industry. The application scenario of microbial electrosynthesis is the first one, how to enhance the output of of methane from the existing feedstocks. So we set up different bioreactors. So the last one, the green bioreactor you see here, is a traditional anaerobic digester. And also the control group with biochar addition, as we have already proved that biochar can enhance the overall methane production yield. And also we have several reactors insert with a pair of electrode. And the best group here is with the pre-treated graphite electrode inserted into the anaerobic digesters. And we found that it has the highest biomethane yield increased in this electrode-assisted anaerobic digester. And also we calculated how much electricity, how much extra electricity we put into the system, and also compared with how much extra energy that we gain from the extra biomethane produced through this system. And we conclude that it can deliver a 6.5-fold energy return on the applied electricity. And the cathode facilitated the biomethane production by 97%, which in other words can reduce 50% of feedstock needs for the biomethane target. And this work was done when I did my PhD in the MARI Center, and it was recognized the notable breakthrough in MARI Research Center 10-year report. As I said, MES can convert CO2 into a variety of bioproducts, not only focus on biomethane. So for other value-added products, for example, the acetate can be a basic biochemicals for further industry application. So for green chemical production, in this work assess the enhanced MES performance in acetate and ethanol production and detail the mechanism of electron transfer behavior at the microbe electrode interface. Electron transportation and utilization efficiency will be a very challenging or research question, especially in this research area. And with this innovative developed cobalt nickel dual metal coated carbonaceous materials, we would be able to enhance the production of acetate and ethanol, and the overall Faraday efficiency, which is in other words the electron utilization efficiency, can be as high as 90.8%. And we conclude the metallic nanocrystals on the electrode surface can enhance the biocatalytic activity, and overall Faraday efficiency exceed most of the literature reviews. Another application scenario is we compared if we if it is feasible to convert CO2 into other more value-added products. For example, so we compare the product's production from lower energy value, such as the methane and acetate, compared it with the other higher energy value content products, such as the ethanol, pure butyrate, and single-cell protein. And we find that through the calculated experimental data, the methane and acetate actually exhibit the highest conversion rate and Faraday efficiency already, depending on the technology's development. And for producing acetate, it requires the lowest specific energy demand, which means that currently it is economic feasible and has the most has the most promising perspective at this moment because of the highest Faraday efficiency. But for single cell protein, we can see the Faraday efficiency is only 10 to 12%, which is lower than the methane or acetate. But actually, the single cell protein shows the greatest responsiveness to Faraday efficiency's improvement. So if the single cell protein Faraday efficiency increased by 20%, we can see the specific energy demand actually significantly reduced from over 1,500 into approximately 3,000. And it shows the greatest responsiveness to Faraday efficiency improvement, indicating the highest long-term optimization potential. And if we calculate the results from an economic perspective, here we did a very simple calculation, the CUF factor, which is the market price of the bioproducts divided by the total cost of input utilities. We assume that it is the electricity. We find that the single cell protein delivers superior economic leverage with an over 6 CFU factor due to its high market value. Another potential scenario application is the biosensor in anaerobic digester reactors. So that's the traditional ADE process. And most facilities actually underload their digesters due to the real-time reliable data due to the lack of the real-time reliable data on feedstock quality and the microbial community health. And if we know that the microbial electrosynthesis process is based on the utilization of the VFAs, and the VFAs can be utilized by the biofilm in the pair of the electrode and the tiny probes. If we did the tiny probes developed based on the MEC technology, and the current density or the electrical signal that we test through this tiny probe will change with the biofilm thickness, which in other words represents the volatile fatty acids concentration level in the process. Then we can use the electron signal to monitor the VFA level in the anaerobic digestion process. And then we can monitor the on-time health of anaerobic digestion in order to instruct the facilities have a higher organic loading rate. Higher organic loading rate means that either gas feedstocks feed into the reactor or more methane production in the traditional process. Yeah, I think I've already highlighted the development of two-stage anaerobic digestion. How can we develop the circular economy systems based on anaerobic digestion, as well as the novel technology microbial electrosynthesis. So here are some take-home message from my presentation. The first one is electrode-assisted anaerobic digestion. We proved in the lab scale that it facilitated the biomethane production by 97%, reducing 50% of the feedstock needs for the biomethane target. And two-stage anaerobic digestion improves the stability and methane yield by optimizing the acidogenesis and methanogenesis separately. The waste-derived biochar, here's an example of the distillery derived biochar, which is a promising low-cost additive for enhancing the direct interspecies electron transfer and stabilizing the anaerobic digestion process. And then MES enables CO2 conversion into valuable biochemicals and biofuels, including the biohydrogen, biomethane, volatile fatty acids, as well as the potential for single-cell protein. But however, the innovative technology, if we want to advance it or for further development, it requires a deeper understanding of the electron transfer mechanisms at the abiotic and biotic interface. So that's all about my presentation. I would be very happy to discuss the topics on anaerobic digestion as well as the bioelectrochemical engineering with all of you. Thank you very much.
Shirley, thank you so much for that in-depth presentation. I'm just blown away with the amount of information there. It was quite a lot there. So thank you so much for your time and yeah, your experience and learnings from your various works. Like for me, the big summary points were moving from a single stage to a double stage digester, and then moving on to the microbial electrosynthesis. And congratulations on your research in making it into the 10-year MARI report. I think that's a real achievement. And I guess from my point of view as well, looking at my own experience in solar plants and utility solar scale, it's interesting to learn about the loading on biodigesters and how to actually work on that later on. So, is a biodigester under pressure? Is it healthy? Is it working okay? So, those were really big learning points for me. So, thank you so much for your time.
Yeah.
Raj, I'll hand over to you to close and we can take it from there unless there's anything else.
Okay. So thanks, Pat. Thanks, Kate, and thanks, Shirley, for your valuable contribution, and thanks to all audience who gave their time from their lunchtime. So we'll see you next time. We'll also organize some similar kind of lunchtime session in the future. And thank you.